Hey Calc BC, welcome to lesson 3.8, volumes of solids with known cross sections, or simply volumes with known cross sections. This lesson is awesome, and it is key to the next several lessons because this is where we take integrals and where we've been working so much with two-dimensional area, and we extend that to three dimensions. So we're going to be talking about volumes and using integrals to find volumes. This idea is really cool. So I hope that through the next few minutes when I'm kind of explaining what this concept of a known cross section is, that you can follow along and maybe even get excited about it. But in college boards course and exam description, we're looking at 8.7 and 8.8 today. We're going to be looking at volumes with cross sections of squares, rectangles, triangles, and semicircles. We're going to look at all of those today. And when you look at each one of these, the essential knowledge is volumes of solids with square and rectangular cross sections can be found using definite integrals and the area formulas for these shapes. And the exact same thing is true for triangular and semicircle cross sections. So we'll be looking at all of those today, and I'll pause for 1 second and we'll move over to the notes. Okay, so here are our notes for 3.8. And you can see at the top of the page here, here's some visualizations of the three-dimensional solids that we're going to be working with today. Let's take a look at this one. So you can see that our x, y axis are now flat on the page. So we got x, this is our y axis here. And in this specific question, think about that we can slice this solid that's being formed, this three-dimensional solid, in this direction. And for every slice, how wide the slice is really changes how big the semicircle is. So this is a semicircle. So this is giving us the diameter of the semicircle. As all the way back here, you can see that a smaller slice means a smaller diameter, and then a smaller semicircle area as a result. And if we combine all these slices, it makes a three-dimensional solid. We can do it with squares, as you can see here. We're going to be doing it with triangles, rectangles, etc. But I found a way to visualize this online that I think will make it even clearer what's going on. So I'm going to pause for 1 second, and we'll switch to that website. Okay, this is an app that some amazing person made using GeoGebra, which is a website that helps with graphing things. And what you can see here is, on the left here is the two-dimensional space that we're looking at with an x and a y axis. And you can see that we have the red curve is our upper curve, the blue curve is our lower curve. And so if I kind of move this line along the curve, if I change what x value I'm looking at, you can see we've got an upper minus lower. And what an integral usually does when we find the area between two curves is it kind of adds together all these little slices, right? If it was a Riemann sum, they'd be bigger bars, but for the integral, it's actually little tiny, tiny, tiny slices that go all the way up to here, and they're adding all of those together, right? So what we're going to do today is talk about what happens when we change this to being three-dimensional. So on the right side of your screen, the xy axis, the xy plane, rather, is this flat kind of gray shape here. So we've taken what was our entire coordinate plane and we've flattened it, and we're visualizing three dimensions. So now we have this z-axis, which is this blue vertical line right here. And if I check the square box, what's happening is a square is being built off of our original coordinate plane. So if we have this purple line, and over here that was this flat line here, let's say that is one side of a square, and the square is coming off of the page. So as I move this dial here and we change which slice we're looking at, you can see that the square might get bigger or smaller depending on how big the original slice was. So if this line is pretty small, the square is going to be pretty small. If the line's bigger, the square is going to be bigger. So you can see it's taller. So what happens is if we add all of these squares together from here all the way to here, what we can do is I can increase this dial and all of the squares start to appear. And what happens is we end up with a three-dimensional shape. So it's not really a shape that we're very familiar with here. This is squares. And the overall shape isn't a cube. It really depends what the base looks like. It's just a whole bunch of two-dimensional squares that are stacked on top of each other. And you know, in this program, it kind of even looks like we've got some like zigzag jagged lines here. But really, this is going to be a smooth kind of curved vertex of this three-dimensional shape. And we've got another one back here. So we've got a flat curved top, a curved side, and a curved other side, and then the base, which is just completely flat, right? So that's what's going on there. That's what this shape looks like. As we add more and more squares, it becomes smooth. If I change the shape to an equilateral triangle, the same idea happens, right? Over here, I'm going to have a smaller triangle. In the middle, I'm going to have a bigger triangle. And if I increase the number of triangles, you can see this time, we just have a point in the middle. You can kind of see if I kind of slice it in half that there's just a point on top. And then we've got those two sides and then the base going on here. So that's what that shape looks like. If we look instead at semicircles, now we have one diameter of the semicircle is on the base, and then half of a circle comes off of it. And again, over here we have a smaller semicircle. In the middle we have a larger semicircle. So if I combine all of these together, this time, similar to a circle, there are no points on top. If I make less, you'll be able to see it better, I think. It's just a completely curved shape. The base, of course, is flat. We're only coming off the page towards the top. And you can see we've got all of these semicircles going on here. So here is the deal. Here's what we're going to be doing. And I just want to think about one circle at a time. What we're going to do, normally what an integral does is when we do an upper curve minus lower curve to find the area between two curves, it's adding together each slice as you go. And it's doing the work for us, but that's what it's doing. So what we're going to have to do today is trick our integral into, instead of just adding the line segment for each slice, we're going to include the area of this 2D shape in each slice. So our integral, instead of just adding together a bunch of line segments, is going to add together areas of shapes. And as we go, it'll add together every single one of these half circles from here all the way to here. And then we'll be able to get the volume of this whole kind of shape, okay? So that's what we're going to be trying to do. So all we have to do is trick out our integral so that instead of just having the line segment, we have an area for each slice, and then solve as normal. So I'm going to pause this screen. I'm going to go back to the notes, and I'm going to show you what I actually mean. Okay, here we are back with the notes, and we've seen some of these shapes now in that program. So let's look at the actual formula. For cross sections of area, A of x taken perpendicular to the x-axis, the volume is as simple as saying from A to B, A of x dx. So A of x is the area of one slice, the 2D area of one slice. We combine it in the integral to turn it into volume. But we can also do cross sections taken perpendicular to the y-axis, just like we could with the area between curves, and it's going to look very similar just with y's instead of x's. Okay? All right, so let's see what this actually looks like down here in the first example. Set up the integrals needed to find the volume of the solid whose base is the area bounded by the graphs of y equals x squared and y equals negative 2x plus 3, and whose cross sections perpendicular to the x-axis are the following shapes. So this is a two-part question. We're going to do A and B separately. So first of all, let's take a look at what this base looks like. So we had the graph of x squared. I'm just going to do a rough sketch here. That's going to be our y equals x squared. And we have negative 2x plus 3. It's going to be something like this. Okay, so that's our two initial functions, and we need to know where they intersect so that we have bounds for our integral. This part is this part is the same as what we would have done in the last lesson. And to find the x values here, I'm going to set these functions equal to each other. So we have x squared equals negative 2x plus 3. X squared plus 2x minus 3 equals 0. And we can change that to x plus 3, x minus 1. So x equals negative 3 and x equals 1. So that means we've got x values of negative 3 and 1 where these intersection points are. Okay, so that's going to be important. Now we are taking cross sections perpendicular to the x-axis. So I'm going to draw in some of those vertical lines here. That's perpendicular to the x-axis. And just like with our regular integral, we know that if our slices are perpendicular to the x-axis, we're going to be using dx. Lucky for us, our equations are already solved with the x's in the equation. They're solved for y equals, so they're in the right form. So now we got to think about what this means down here. Okay, so in a normal problem, if we were just finding the area between the two curves, what we would do is area equals negative 3 to 1, the upper, which is the negative 2x plus 3, minus the lower, which is the x squared dx, right? But we don't really care about that. I mean, I might just want to simplify it a little bit because we are going to use this. But we didn't even have anything that, no like terms combined anyways. But there, that's a little bit nicer. So this is the area between the two curves, right? So if I plug in any x value into this, it'll tell me the length of that line segment in there. So if I plug in negative 1, it's going to be telling me the length of this line segment in here. If I plug in 0.5, it'll tell me the length of that line segment. That's what this is saying. If we want rectangles of height 4, the first thing I'm going to do is sketch what this is going to look like. So here's a rectangle. The rectangle has a height 4. And what we want to think about is that each one of these slices up here, so maybe I can shade this one in right here. That length, that line segment, is going to be serving as the base of each rectangle. So picture that there's literally a rectangle coming off of the page right here. And it has a height of 4. It's coming straight off the page. So the whole shape has a height of 4, and the base is whatever this length is, okay? So I guess the question is, what is the length of the base? And we already figured it out, right? We can find each individual rectangle's base if we wanted, but we could also just say, oh wait, why don't we just say negative x squared minus 2x plus 3 is the length of the base? Because that accounts for all of the different lines, right? That accounts for all of the different slices. So to find our volume, let's think about this formula. It's going to go from A to B, A of x dx, and A of x is the area of a specific cross section. So we're going to go from negative 3 to 1, and then let's think about the area of a rectangle, right? It's 4 times negative x squared minus 2x plus 3. It's the height times the base. So that's going to give us the area of each rectangle. And when we put it into the integral, it populates the entire shape and tells us that the volume of the overall shape, the overall 3D shape. So let's see what we can do here. We can do this by hand. So we're going to go from -3 to 1. If I distribute the 4, I get -4x squared minus 8x plus 12 dx. And then I'm going to start to do the derivative, the integral. So I do -4x cubed over 3. This is going to be x squared over 2, but there's an 8. So now it's going to be minus 4x squared plus 12x. And that's going to go from -3 to 1. So let's see. Well, if I plug in 1, it's going to be -4 thirds minus 4 plus 12. If I plug in -3, it'll be -4 thirds times -3 cubed minus 4 times -3 squared plus 12 times -3. And if we combine all of this, we end up with 128 over 3. And that's a volume, so you won't necessarily need to include units cubed, but it is in cubed units, right? That's what we're talking about here. So I'm going to include that so that you can really see that. 128 divided by 3 is 42.6-ish. So if we think about this shape, I think it makes sense that 42.6-ish seems reasonable for the volume with rectangles of height of 4. And it goes all the way from -3 to 1. It just kind of makes sense that could be the volume. And it is, okay? So that's what's going on there. Again, we found the area of each cross section where the x's are still built in so that each cross section is accounted for. We plug it in to our integral, and then we solve. Okay, so let's try letter B. Semicircle. So semicircle means half of a circle. I'm going to sketch that over here. And remember, just like in the diagram at the top of the page, these two, and just like what we saw in the app on the website, the semicircle is half a circle that is coming up with the diameter is what was originally the line segment in our 2D area. So now the diameter is our -x squared minus 2x plus 3. So how are we going to find the area of half of a circle here? So we know that area equals pi r squared. But we only have half a circle, so it's going to be 1/2 of pi r squared, right? Hopefully that makes sense. We have half circle, so it's half the area. But we have another issue, and that is that our r is not just -x squared minus 2x plus 3. That's the diameter. So we actually have 1/2 pi times that whole thing divided by 2. So it is, I could put it in brackets, 1/2 times -x squared minus 2x plus 3 squared. Okay, so it's important that the 1/2 is in with this expression before we square, because all of that is building the radius. And yeah, there you go. There you can see that. We could distribute that if we wanted. For this specific question, it gets a little bit complicated, so I am just going to do this in the calculator. But let's write out the volume formula first. So our volume is going to be, once again, we're using the same shape. So it's still going to be from -3 to 1. This time, we want the area of one slice to go in the integral. And the area is going to be this half of a circle's area. So it's going to be 1/2 times pi times bracket 1/2 of -x squared minus 2x plus 3 squared dx. Okay, so again, I'm going to do that on the calculator. So I'm going to type that in as math 9 from -3 to 1, 1/2 times pi times parenthesis 1/2, parenthesis negative x squared minus 2x plus 3, close both parentheses, square dx. And I end up with 13.404, and that's what I got earlier, so I know I am correct, unless I made the same mistake twice, but I don't make mistakes. That's not true. And so this time, got 13.404 units cubed. I said the first one was 14.6 something, sorry, 42.6 something versus 13. So this is significantly smaller of a shape than the first one, but that makes sense because this is rectangles and they all have a height of 4. This is semicircles and the radius is constantly changing. So up here, that's going to be a really small shape, but for the rectangle, it still has a height of 4, even all the way up here. So it makes sense that that's going to be a lot bigger in the first part. But there you go. That is how we do that question. We have a couple more to do because we still got to figure out how we do an equilateral triangle and how do we do a square as cross sections. All right, so let's keep going. Next example. Set up the integrals needed to find the volume of the solid whose base is the area bounded by the circle x squared plus y squared equals 9, and whose cross sections perpendicular to the x-axis are equilateral triangles. Okay. This is going to be really important for us to remember going into the future. The area of an equilateral triangle equals s squared times √3 over 4, where s equals the side of the triangle. Remember, equilateral triangle means that all 3 sides of the triangle are the same length. We are only going to have the base, so it's going to be helpful for us to know that this is the area of the overall shape. We could have figured that out using the Pythagorean theorem, but we don't need to. So let me be consistent. I use blue, so I'm going to, up here, I'm going to draw this. So if we have a triangle here, the base is going to be our slice from the 2D region. And we're going to have to figure out what that length is, given that the formula is x squared plus y squared equals 9. But anyway, once we figure that out, it's going to be the area is going to be √3 over 4 times s squared, which is the same thing as s squared √3 all over 4. And what that does is it kind of splits the base in half, thinks of it as 2 right triangles, finds the area of each, and then adds them together. And this does that work for us. So that's what all this formula is doing, is just calculating that for us. But anyway, let's get back to the question. So if we have a circle with this formula, you might remember the formula for a circle is x squared plus y squared equals r squared. So here r is 3. So really this is just saying that we have a circle with a radius of 3. This is going to look like this. Okay? And the cross sections are perpendicular to the x-axis. So we're going to be like this. And here's an example of a line segment that could be thought of as the base. So we've got triangles coming off the page here at each one of these slices to make a 3D shape. So it's going to start pretty small over here. It's going to have a point on top that grows as the base is larger, and then it's going to shrink again. So it's going to have a pointed top that grows and then shrinks from left to right. And we saw that at the beginning if you want to go back and watch that part of the video. But let's keep going. Okay, so the formula here was x squared plus y squared equals 9. We can't plug that into an integral, so I'm going to have to solve this for y, since we're going to integrate in terms of x. We got y squared equals negative x squared plus 9. Y equals plus or minus the square root of negative x squared plus 9. So the height of each slice, or the length of each slice, The positive square root is going to be the top half of this circle, and the negative square root is going to be the bottom half of this circle. So we could think of it as the top half minus the bottom half. Remember, it was minus negative because the top part was positive, the bottom part was negative. And this is going to become minus and negative. So it's really plus. So this is really 2 square roots of negative x squared plus 9, right? Because it was this plus itself. So we have 2 square root of negative x squared plus 9. I'll do something about that shadow. So let's set up our volume. First of all, so this is what's going down here. Oh my gosh, now you can't see that. This is what's going down here. 2 times the square root of negative x squared plus 9 is the base of this triangle. It's also the length of this side and the length of this side. But all we need to do is plug that in for s. The length of one side gets plugged in for s, and then we can solve. So we've got the volume equals the integral from -3 to 3, right? Because that's our left bound and our right bound of our integral. And inside, we've got root 3 over 4 times the s, which is, I'm going to put this in brackets, 2 square root of negative x squared plus 9 squared, because the x was squared, dx. There you go. And this question's just said, set up the integral. So we don't even need to find the answer. That is the answer. But we could type that into a calculator if we wanted. We might even be able to do it by hand since the square and the square root are going to cancel for part of this. So that is doable. If you want an extra challenge, you can do that. But the question didn't ask us to. It just said to set it up. So we did it. Okay, so that represents the volume of the solid. Okay, last one. The base of a solid is bounded by y equals x squared, y equals 0, and x equals 2. All right, so this one is giving us 3 different equations to start. For this solid, each cross-section perpendicular to the y-axis is a square. Okay, interesting. So let's figure this out. The base of the solid is bounded by y equals x squared. It looks like this. Y equals 0. Okay. And x equals 2. So we've got this. X equals 2 is over here. Y equals 0 is here. Okay. So we've got a triangular region going on right here. So we want cross sections perpendicular to the y-axis. So it's going to be like this. And each of those little tiny slices is the base of a square. So I'm going to sketch a square down here. And I'm going to, as always, make one orange slice there and make the base of this orange so that you can see that that is representing this, and think of it as square slices coming off of this page to make a 3D shape that's going to have a certain volume. And this time, because we are perpendicular to the y-axis, we have to think about everything in terms of y. So if I plug in 2 for x here, I get 4 for y. So this is intersecting at 4, I believe. And down here, we're at 0. Okay, so it should be, yeah, 1 squared is 1, 2 squared is 4, yeah. Okay, so on the y-axis, we're at 4. So this is going to be a volume from 0 to 4. The part of the curve to the right goes first, right? Actually, let me just figure it out down here first. So to the right goes first, and to the right is this x equals 2. So we have 2 minus whatever this part of the curve is to the left, which is y equals x squared, but I want it to be in terms of y. So I'm going to have to solve this for x equals, and so I get plus or minus the square root of y equals x. And so think about that. The positive part's going to be this half of the curve. The negative part's going to be this half of the curve. So I only really care about the positive part. So it's going to be 2 minus the positive square root of y, which ends up being 2 minus square root of y. So if that's the base, that's also the height. So the area of each of these squares is going to be 2 minus root y squared. Okay, and so I'm going to come back over here. I already set up the bounds from 0 to 4, and now I have the area of each square. So it's going to be 2 minus the square root of y squared dy. And that is making a square at every single one of these slices, adding them all together to get a 3D volume. So that's how we do that. And this question also just said set up the integral. So we set it up. All right, and what you're gonna see when you get to the worksheet here, because that was the last question, what you're gonna see when you get to the worksheet is that you have just seen how to find the volume when the cross-section is a square, when it's an equilateral triangle, when it's a rectangle, and when it's a semicircle. But those are not the only shapes that we know of, right? So sometimes on the AP test and on quizzes, you might be asked to find a volume when the cross-section is a different shape. And that happens a couple times on the worksheet. And all you have to do is think about the area formula for that shape and plug in the proper base given in the question, given the formulas in the question. So it's a little bit tricky, but I have faith that you can do this. And please let me know if you have any questions. And good luck. All right. Have a great day. Thanks.